BM25 can miss a relevant passage when the query uses different words. Sentence Transformers SPLADE learns sparse term weights that expand the match without turning retrieval into an opaque, dense vector. After this, you'll understand how to assemble a pipeline that finds matching passages and exposes the weighted words behind each match. I'm Professor Pine, teaching AI foundations with simple Python. Search breaks when users and documents use different words. BM25 is fast but literal. Dense vectors are forgiving but opaque. SPLADE sits in the middle. It outputs sparse, high-dimensional vectors, where each active dimension maps to a real vocabulary token and carries a learned weight. That gives two concrete benefits: lexical expansion so related words can match, and interpretability so you can show which words actually drove a hit. Practically, SPLADE is a retrieval model you pick when you want better recall than BM25, while still being able to inspect why results ranked as they did. It works from a few thousand passages up to millions, because the sparse vectors plug into normal retrieval pipelines. The cost to watch is index size and scoring time. The more active dimensions you keep, the more evidence you carry, and the more storage and compute you use. A helpful mental image: the model turns your short query into a shopping list of weighted words. A query for vehicle might light up car, engine, and drive. That allows a passage that only says car to surface for vehicle. The trade-off is simple. More dimensions mean stronger evidence and bigger indexes. Fewer dimensions save resources, but risk losing matches. We will build a tiny demo pipeline. You'll see one query, 3 documents, how SPLADE represents them, how the system ranks documents, and how to read the actual words that produced a match. That should make the idea concrete enough to scale later. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let us start by turning a single query into a SPLADE sparse vector, so you can see how the model expands the query. This snippet loads Sentence Transformers SparseEncoder and turns one plain query into a SPLADE sparse vector. BM25 starts from exact terms, so the first useful shift is seeing the query become a weighted sparse vocabulary object instead of a bag of words. SparseEncoder selects the SPLADE model, and similarity FN name set to dot makes later model.similarity calls use dot product scoring. Encode query keeps the retrieval role explicit, which matters when a model has query-specific routing or prompts. The output shows how many vocabulary dimensions are active, giving a first feel for learned lexical expansion. That worked for a single query, but we need document vectors before we can retrieve. Let's encode a handful of passages so the system has something to search. This example uses Sentence Transformers SparseEncoder .encode document to create sparse vectors for 3 searchable passages. A search system needs document vectors before any query can retrieve anything, and here docs is intentionally small enough to read at a glance. Doc.ides gives each passage a stable label, while docvex stores the SPLADE representations created for retrieval. SparseEncoder.sparsity.docvex summarizes how much of the huge vocabulary space is actually non-zero. The output shows the average active document dimensions, which connects sparse retrieval to storage and indexing cost. With query and doc vectors ready, we need to score and pick the best match. Let's run the sparse.product and inspect the top result. This code ranks the toy passages with Sentence Transformers SparseEncoder.similarity and returns the best document ID. The viewer pane is visible here. The query says vehicle, while the most relevant passage may use car, engine, or start instead. Model.similarity, qvec.docvex, compares the sparse query vector against every sparse document vector, and scores.argmax selects the highest scoring passage. Because similarity fn name was set to dot on model, this is a sparse dot product retrieval step rather than a dense vector lookup. The output shows the winning doc ID and score, proving the index can rank passages without exact query wording. We can rank, but can we explain why a document won? Next, let's decode the highest weighted vocabulary items that led to the match. This snippet uses Sentence Transformers SparseEncoder, decode, to expose the strongest vocabulary weights behind the retrieved passage. Dense retrieval can be useful, but it often hides why a passage matched, which makes debugging search results harder. Model.decode, docvex, top k equals 5, turns active SPLADE dimensions back into readable vocabulary tokens, and docterms selects the tokens for the current top result. Those tokens can include exact terms and learned expansions, so treat them as retrieval evidence rather than a sentence summary. The output shows the top weighted vocabulary items, making the match easier to inspect. Interpretability is great, but production systems also care about index size. We should try capping how many active dimensions we keep. That shows the memory versus quality trade-off in a tiny loop. This example reruns the mini search with Sentence Transformers max active dims to cap each sparse vector. Sparse vectors are interpretable, but a production index still cares about how many non-zero dimensions must be stored and scored. Encode query, max active dims 32, and encode document, max active dims 64. Keep only the strongest active dimensions before model.similarity ranks the passages again. Increasing max active dims keeps more lexical evidence, but can cost more memory and scoring work. Decreasing it makes the representation smaller, but may remove useful matches. The output shows the compact winner and the capped active dimension count, forming a tiny baseline search loop. Applied to a real system, you would replace the 3 toy passages with a corpus like a passage collection and compute document vectors once. You would store non-zero dimensions in an inverted index or compressed sparse format and run the same sparse dot product at query time. The same decode step helps audits and result explanations in production. In short, SPLADE produces sparse, token-aligned vectors that expand query wording while remaining human interpretable. Use it when you want better recall than BM25 and need to explain why results matched. Watch storage and scoring costs. Cap active dimensions to control resources. A practical next step is to tune max active dims on a real passage collection, for example MS Marco passages, and sweep values to measure recall versus index size. That single parameter sweep will show the memory and ranking trade-offs most directly for this pipeline. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.